So the first algorithm we're going to look at is selection sort. Selection sort is a really simple algorithm that used to sort data elements. Its simplicity is really evident in its implementation difficulty. It's really easy to write the code for this one. However, as an actual sorting algorithm, it's pretty inefficient. The algorithm is described as below. First, select the smallest element in the array, so you just kind of search linearly through the array. Swap that element with the first element in the array, and then you search for the second smallest element in the array, and you do that by doing a linear search again. You swap that with the second element, and you continue until all the elements are processed and the array is sorted. So as an example, I've got an array here with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And as you can tell, at the moment it's a bit of a jumble up. So the first thing I do is I go through my array looking for the smallest value. And the way I actually do that is I say, okay, the first thing I've seen is 34. Is 15 smaller than that? It is. So then I hold 15 in memory. And then I check that against every other value. So say 15 versus 17, is 15 smaller? It is, so I keep 15. Move on, 15 versus 91, is 15 smaller? It is, so I keep 15. And that's how I find out what the smallest element is. Okay, and so then that 15 becomes my first element, and I've had to check it against everything. Now I'm looking for my second element. So I'm looking for something that's bigger than 15. Okay, so the first thing I set it to is just 34, which is in the second element there. I then check that against 17, find that 17 is smaller than 34, so I move that into the second element, and then I have to check that 17 against every other number in the array to check it's smaller and to check that I've got the correct second element. So you can see that every time I'm doing a full pass through the array. The algorithm carries on, setting the third position, then the fourth position, the fifth position, and eventually we swap the sixth position, and we carry on until all the elements are processed. So for every single element, we've had to look through the full array and find out what the smallest is and the second smallest by doing comparisons between two numbers. So this is really not a very efficient way to actually search an array. Easy to program, not very efficient. So when implementing a selection sort, what we do is we search for the smallest element in the array for each element position, and we do that by doing the comparisons I talked about when I talked you through the algorithm. Searching for the smallest element in the array runs at O(n) time, because every single time you've got to go through the whole array to see what the smallest element is, or the second element, second smallest, so forth. Doing so for each element in the array, so doing that every single time we're setting a position in our sorted algorithm, sorted data, means we have to do this n times. The swap, we actually swap the data for the constant time, so that's big O of 1. Therefore, selection sort's complexity is n times n, which is n squared, okay, where n is the amount of data you're trying to sort. So that's our first sorting algorithm, that's selection sort. I'm going to ask you now to try that out with your playing cards, and then we'll come back to our second sorting algorithm, which is going to be insertion sort.